Okay, thank you. So now I would like to give a last example, which is in some sense the worst. So the last example is due to a former student of Antoine Chamberloir. So this example is constructed as follows. So you look at the variety V, which is the Hilbert scheme of subschemes of dimension 0 on the degree 2 over P2. Okay, Hilbert scheme of points of degree 2 in P2 over Q. Then, well, there is a way to describe it. So you can look at it the following way. So, well, you have P2. Well, you look at pairs of points on P2. So P2 square. And then you take the quotient under the action of z over 2z. Of course, you get something which is singular along the diagonal, but then you blow up the diagonal in it. Blow up the diagonal. Well, you can also show it by blowing up the diagonal here. You get, well, blow up along the diagonal of P2 square, and you get something, a square like that. All right. Then, so let me do it. Well, the image of the diagonal there by delta bar, and I need a few notations, so I call that F and this map G, and then I'm going to use open set U naught to be V minus the inverse image of the diagonal. Right, then the point is that if you look at the following subset, oh, let's call it T. So the following subset, which is inverse image by F of the image of the rational points in P2 square intersected with, so I remove the point on the diagonal. Then this set is a Zariski dense sin subset of V, because you can see it through the square, so it is a sin. And the theorem, a consequence of the theorem of Cécile Lerodulier, is the following, namely that if you look at the cardinal of the points of height less than b which are contained in T divided by the total point, the number of points of bounded height on U naught, then this converge to a constant, to an explicit constant, which is strictly positive. But for any closed subset, a strict closed subset, the number of points in F is negligible. Well, I should intersect with U naught. Yeah, let me write it like that. Intersected with T with height less than B is negligible. So why is that surprising? So you see in the example of Peyre and Schinkel, in some sense we were with the problem that all the fibers where the rank of the Peyre group was too big were accumulating. So there were too many points on each of these fibers. This is more tricky because there are too many points in the thin subset. So in that sense that the contribution of the thin subset is not negligible. But if you look at closed subsets in T, you do not get anything accumulating. So it's not the union of some accumulating closed subsets. So it shows that you really have to look at thin subset. I mean, this one you cannot obtain as a union of closed accumulating subsets. And it makes it really more difficult to interpret. All right. So, well, nevertheless, it's also very nice because she shows that if you look at the complement, which was not obvious in the example, which is still not known for the counterexample of Peyre and Schinkel, she proves that if you look at the complement of this thin subset, then the number of points you get is precisely the one which is expected. So this means that, okay, on the thin subset, you have too many points, but on the complement, the behavior is precisely the one which was predicted. And also, it was the first case in which it was proven that on the complement of the thin subset, you get what is expected. So, I mean, it's a very nice result. All right, so the conclusion of all that, of all these examples, so far, of course, so in all known cases, if omega v minus 1, let's say, is big enough, so big enough is a condition which is slightly stronger than big. There exists W, which is a complement of a thin subset in V of Q such that if you look at the distribution on the complement of the thin subset, so the distribution associated to the point of height less than b on W converge to mu of v as b goes to infinity weakly. I should stress, that it's still rather optimistic. Even in that case, where we know that the total number on the complement of the thin subset is the correct one, the fact that it is equidistributed was not yet proven. Okay, but still, for various reasons, when you get the right, in each time you get exactly the precise number of points which is expected. If you try hard enough, generally you get equidistribution. The two are related in a very strong way. I won't go into that today, but the fact that the total number of points is the one expected is directly related to that. If you don't have equidistribution generally, this means that the total number of points cannot be the expected one for all I, in some sense. All right. So, okay. So this is currently the hope we have is that if we remove a thin subset, then we get what is wanted. The problem we still have is how do we find this thin subset? How to find problem well, okay, so before I go into that, I would like to make a short remark. May I ask, why am I using always heights which are relative to the anti-canonical line model? So let me just make a remark about that. The point is that if L is different from omega v minus 1, then there is a generalization but the situation is even more complicated. So this is due to Peyre and Schinkel. But the point is that in general, you get fibrations and you have measures which are sums of measures on the fiber. So let me give an example. If you take P1 cross P1 over Q, let's say, and you take a height relative to L, which is not a multiple of omega v minus 1. L ample. Well, if you look at the measure given by the points of bounded height, and if you look at the limit, then you will get something which is the sum for P belonging to P1 of Q of, let's say, I don't know how to write it, but so there is a constant Cp, and then the measure on the fiber. So let me write it, the measure on the fiber as, well, it's slightly improper, but as P times the mu measure on P1. Or, of course, depending on which side you are, it can be also Cp of mu of P1 times P. So by this, I mean that the situation is as follows. Either you will have a distribution like that, where you take the sum of the contribution on each vertical line, or you will have a distribution which is like this, where you take the sum over all horizontal lines. On the all, what you get is a fibration, and then you have to take the sum of the measures on each fiber of the fibration. So you can make it quite general, but then it's more complicated. All right, so for the rest, I will stick to the case where it is omega v minus 1. But I want to go back to this problem. And in fact, to be more precise, what I would like, I mean, of course, there are good points, the one you want to count, and bad points in some sense. And you would like to have a way to characterize good points and separate good points from bad points. So up to now, the link with Arakelov geometry was limited to the height. But now it's time to go back to what I said at the very beginning, namely that I wanted to use slopes. So let's try to see what slopes can tell us about the problem. So I'm going to use slopes à la Bost as they were described in the lectures of Eric Godon. So let me make a few quick reminder. So let's start with slopes for a vector bundle with an adelic norm over the spectrum of K. Right, so remember that, so I assume that I have this data. So E is a K vector space, and I have an adelic norm on it. Therefore, for any subspace F in E, I can define an adelic norm on it by using the restriction of the norm. And therefore, I get the degree of F using this norm. Right, then remember that what we consider as a convex hull of the set of given by the pairs dimension of F, degree of F, for F in E. So the point is that this thing is bounded from above. So the picture which you have already seen is like that. So if you follow the definition, realize that the degree of the null vector space is 0. And then somewhere you have the point dimension of E, degree of E. And then in between you have points. Eric has shown you already this picture with things like that. And you take, the point is that it's not bounded from below, it is bounded from above. And if you take the convex hull, you get something like that. Right. And you define, then, well, I'm not sure of the notation, but let's call it ME, which is a map which goes from, was it PE? I don't remember. PE, yeah. To R, which is simply given by PE of T is the sup of the y such that Ty belongs to PE. And then the slopes, mu I of E. Well, I define them as PE of I minus PE of I minus 1. So the point is that, of course, if you look at this function, PE, so the graph of PE, maybe I should do it in another color. So this is PE. So it is partwise affine. And the slopes are precisely the slope of the segment between I minus 1 and I. So by definition, you have that the slopes, since it is convex, you have that the slopes are decreasing. So mu1 of E is bigger than or equal to mu2 of E, and so on, which is bigger or equal to mu n of E. So note that, okay, this you can have equality. Two successive slopes with this notation can be equal. Right, and then, okay, so this is some data, some natural data, which, as we have seen, is very useful, which is attached to a vector bundle over the point with an adelic norm. Okay, also I should have said, sorry, I forgot, that the degree, of course, of E itself is the sum of the slopes from 1 to the dimension of E of mu I of E, also by definition. Right, so now let me use this, but in the context of a variety with an adelic metric. So remember, in my talks, I'm using the terminology adelic metric only for adelic norms on the tangent bundle. So yeah. Then I will introduce the concept of freeness. So assume that V is a nice variety with an adelic metric. Then this means that for any rational point in V, if you look at the tangent space of V at X, well, it comes with an adelic norm. And therefore, you can apply the concept of slopes to it. So you define mu I of x to be mu I of the tangent space of V at x. And if you use the stupid remark I gave here, well, it implies that you get that mu1 of x is bigger than mu2 of x, and so on is bigger than mu(n) of x. And also you get that the degree of the tangent space of V at x is equal to the sum for I going from 1 to n, the mu I of x, where I should have said n is the dimension of V. But the degree of T of x of V, well, this is nothing else than the logarithmic height defined by the metric. So this is the degree of lambda n of Tx of V, which is, in fact, the logarithmic height where h is a height relative to the omega v minus 1. So in some sense, so if you look at that, this gives that h of x over n is the mean of the slopes. Right, so the point is that, okay, you get the height, but you get extra data. And the idea is to try to use this extra data. So, of course, once you have this extra data, you want to understand it, which is not that easy. So let me introduce an invariant. So the freeness. So this invariant is a little bit inspired by the geometric counterpart of that. So the freeness of a point is, so L is for liberty. So it will be mu n of x times n over h of x if mu n of x is strictly positive and it is 0 otherwise. All right, so what can we say about this L of x? So more generally, I may also write L of E to be mu n of E dimension of E mu n of E if mu n of E is strictly positive, 0 otherwise. Okay. So what do I want to say about that? So first of all, the first obvious remark is since h of x over n is the mean of the slopes, you have an obvious inequalities which says that mu n of x is smaller than h of x over n, which is smaller than mu1 over x, mu n of x, sorry. So, so this implies that in any case, L of x belongs to 0, 1. So to say that it is 0 is exactly the same as saying that mu n of x is less or equal to 0. Obviously. More interesting to say that L of x is equal to 1 means that the smallest of the slopes is equal to the mean, which is exactly the same as saying that all the slopes are the same. Which says that, well, if you look at the Harder-Narasimhan filtration, there is no intermediate subspace. So how to say? This means that Tx of V is semistable. I don't think you have seen any. Yeah, I think the only example we gave to you was Zn. So for the usual Euclidean norm. Well, there is another one which is nice and which shows that it's not only like that, which is the hexagonal one. So if you look in dimension 2, you look at the hexagonal lattice. And this one is semistable as well. Well, another way to describe that, I mean, for in dimension 2, up to rescaling, well, up to rescaling the lattice in dimension 2 well, a lattice is isomorphic, Euclidean lattice is isomorphic to Z plus Z tau in C, where, as you know, tau belongs to the domain, the fundamental domain. So this means that the module of tau is bigger than 1, and the imaginary part of tau is positive, and the real part of tau belongs to, let's say, -1, 1. Well, let's take the closure. It doesn't matter much. So it looks like well, of course, I won't be able to do a nice drawing, but okay. So it's more or less like that. So you take a lattice which is like that. 1 on tau. And to say that the lattice is semistable, is equivalent to say that, sorry, the imaginary part of tau is less than 1. So this is the lattice is where tau is there. Okay. Okay, yeah, so now let's go back to the geometric setting. So, well, I should have said, I guess, that for a curve, well, we are in dimension 1, so nothing is happening, so the freeness is always equal to 1. But for a surface, then we are in dimension 2. So in fact, let's say over Q, then in some sense we have two invariants. So we have two invariants which somehow describe the lattice corresponding to Tx of V, the Euclidean lattice corresponding to Tx of V. So the first invariant is, of course, height. So P goes to the height of P, which more or less gives the covolume of the lattice. And the second invariant is precisely, well, I should have said that this was the same as the half-plane, Poincaré half-plane quotiented by SL2 of Z. No. PSL2. So, okay. Yeah. I hope I'm not doing a stupid mistake, but anyway. So, to a point P, I consider the class of, well, tau P, where tau P corresponds to the lattice. The Euclidean lattice defined by the tangent space at P. So this one, we are used to it. I mean, looking at the height, okay. Well, this one is, in some sense, not much looked at. So anyway, so how can I express the freeness in that case? So the freeness of X is equal to 1 if the imaginary part of tau of X is less than 1. As I said before, this is the case. This is the characterization of something which is semistable. It is equal to 1 minus the logarithm of the image of imaginary part of tau x divided by the logarithm of h of x. If this is positive, if and it is equal to 0 otherwise. Okay, so the point is that, okay, if you think, well, the first idea is that, the image, the lattice you obtain here should be quite random. There is no reason for it to be very particular, a priori. Of course, we shall see that it is not the case. It's not random at all. But if it were random, then you see that the condition as the height goes to infinity, the condition is that to have a freeness, which is strictly positive, the condition is that the imaginary part of tau should be less than the height, somehow, up to some constant. So there are less and less conditions. There are more and more lattices which are acceptable in some sense. So you would think that, looking at that, the first time, you would think that, well, the freeness of x should be always strictly bigger than some epsilon, most of the time, at least. Well, in fact, this is not true. So this is what I want to explain later on. So let me give you now some properties. So first of all, how much does it depend on the choice of the metric? So if I choose two metrics for my variety, what is the change for the freeness? So for that, let me introduce a lemma. So if I have a morphism of vector bundles, with adelic norms, well, then there exists a family such that, so this is more or less what I already explained. Okay. For any w in the set of places of k, for any x in V of kw, for any y in the fiber, we have that phi of y prime w is less than lambda w norm of y. And so this I explained already on the set of lambda w, the set of w, sorry, such that lambda of w is different from 1 is finite. So I explained that already, but a consequence of that is that yeah, consequence. For any x in V of k, so V with two metrics. For any f in Tx of V, we have that degree of f minus the degree prime, so for the second metric of f, is less than c. So I should have said. So of course the constant c will depend on the matrix, I mean. So therefore, as a corollary, we get that L of x, yeah, let's be more precise. L prime of x minus L of x is less than some constant divided by h of x if h of x is strictly positive. So the difference between the two freeness goes to 0 as the height goes to infinity. So it depends on the choice of the metric, but not too much. Right. Okay, so that's the first property. The second property I want to speak about, and probably the last one for today, is to relate these two curves. So as I said, the inspiration for all that comes from geometry. So, and more precisely, from the study of morphism from P1 to V. So what is the relationship between these things? So the point is that there is a way to describe that a curve, so a morphism like that, is very free. This means that can be moved around in a strong sense. And the criterion for that is to look at the pullback of the tangent bundle by phi. So this is a vector bundle over P1. But the point is that a vector bundle over P1 can be split, well, is isomorphic to a sum of line bundles. So in fact, we can write as a direct sum for I going from 1 to n. So again, n is the dimension of the variety of O of AI. And this is more or less unique if you impose that the AIs are decreasing. And in fact, these AIs are in some sense the slopes of phi. So in fact, I denote mu I of phi to be AI. And also, I'm going to define, well, I should say that by definition, the degree of phi relative to omega v minus 1, which is in fact the degree by definition of phi star, phi upper star of omega v minus 1, is the sum of the slopes. And therefore, I define L of phi to be, well, mu n times mu n of phi divided by the degree if mu n of phi is strictly positive and 0 otherwise. Okay, then what is the result I want to state? Where am I? Right. So again, as you see, these freeness for morphism from P1 have similar properties. So for example, the freeness is between 0 and 1 and so on. And the freeness L of phi is strictly positive if and only if phi is very free. Right, so now position is as follows. So as before, let phi be a morphism from P1 to V. Then if I look at the freeness of the image of a point in P1, then this goes to the freeness of phi as the height of x goes to infinity. Well, the point is that the speed of this convergence depends on phi. So, of course, if you take a point in V, it can belong to many rational curves. So, but still. So already it says something. It says that if you have in your variety, if you have a curve which is not very free, so for which L of phi is equal to 0, then if you take rational points on this curve, their freeness are going to 0. All right. So let me sketch the proof of that. And I finish with that. Otherwise, Gael will not be happy. So I write as before as a direct sum, exactly as I've done here, with decreasing AIs. Then, of course, of this, I can choose, well, I have two natural norms on that. Here, I have the pullback of the metric. And here, I have the direct sum of the natural norms, well, of the norms you choose on P1. You take the norm, you take the tensor product, it's well defined, so you get something, and you have another norm. Since you have an isomorphism, this means that you have, in some sense, the same vector model with two different norms, and therefore the difference is bounded. Well, so this means that if you look, so if you take the freeness corresponding to this pullback with this norm, you get exactly the freeness of phi of x. If you compute the freeness on the other side, well, you get ANN over the sum of the AI, that is L of phi, a constant. And you get that this is less than some constant, which depends on phi divided by the height of x. So this gives a result. So this simply use that, I mean, the fact that the freeness does not depend too much on the choice of the metric. Okay. So I think I'm going to stop there for today.